Afternoon session. So the first speaker of this session is Everton Medeiros from Universidad Estatal de Sao Paulo, I guess.
Yes.
Okay, and the title of the talk is Local Control for the Collective Dynamics of Self-Propelled Particles. Okay, please.
So, thank you very much, Albert. So first, good afternoon, everyone. So first of all, I would like to thank the organizers for changing the program to fit me in, so last minute. I also would like to thank Professor Feudel for giving me the opportunity to speak here today. So the title of my talk is Local Control for the Collective Dynamics of Self-Propelled Particles. So as the title suggests, so we are dealing with physical systems. So this means that we have the physical state space. So we have positions and velocities in our system. And besides that, so these systems, they are spatially extended. So in our case, this means that they are composed by multiple interacting elements, and these elements, all of them, each one of them occupy different position in space. Therefore, we have a system which is spatially extended. So there is a length scale in the system, right? So altogether, so this system, they evolve in time, and so in their time evolution, so they are dynamical systems, and in their time evolution, so they converge to the so-called self-organized states. So those are states of the collective, and so it's important that these states often they are associated to some function perturbed or performed by the collective. And so given these functions, it arises the necessity or the need to control these states. But unfortunately, controlling this state is very challenging because of this extension in space. So this length scale is difficult to know where to apply the control in these systems, especially because each element, they interact with each other in a non-linear way, right? So it's difficult to see where to apply the control because it's not viable to apply the control in the whole system altogether. Therefore, one needs to know where to apply the control. So that's the big problem in the literature. So here I'm going to show you, I'm going to consider a system of interacting particles, and I'm going to show you that in this system, by performing local interventions in only one particle, so it's possible to cause global transformations in the system. So that's what I'm regarding as control. So these interventions that I'm going to apply, and then we are going to see some global transformations. So this is in a system of particles. So this is a bit of the context here. So now that we have this in mind, so I would like to specify the research that underlies this question. So in the end of the day, what we want to know, so given this system, they are spatially extended, what we want to know, what are the conditions of interventions that we could do locally that enables these interventions to progress in the system, to percolate the system as a whole. So that's the overall question underlying this research. So by the end of this talk, I hope to have some insights about this question, okay? So usually I have here some motivation, but today I don't have much time, so I will jump into the model I'm using. So as I said, I'm considering a system with particles interacting. So these particles, they perform movement in the plane, right? So then the physical state space, as we see here, position and velocity, they are in 2 dimensions. So here I have the equations describing the movement of the particle. So we can see that variations in the positions of the particles is the velocity. This is the easy one. And then we see also that the variation in time of the velocity is given by a function that we see here. So let's look a little bit into details of this function. So in the first term here, this is alpha v. So this is a positive term. So this means that these particles are receiving energy, right? So the idea of this model is to mimic some biological system. And this term here is mimicking the internal source of energy of every biological being that we may have there. Could be, for example, birds in a swarm, could be also bacteria in a community, or amoebas, for example. And they have this internal source of energy, and this alpha corresponds to mimic this behavior. And in the second term, this is a negative sign here, this beta term. So this is a dissipative force. So this means that the particles, they are interacting with the environment, and they are under the effect of viscous forces of the environment, and then they are losing energy to the environment. And this beta goes with the third power of the velocity. Okay? Then finally, we have the third term. So this is the interaction term. So this is one particle converses with the others. So this is prescribed by a potential, as we see here, this U function, and this U is the Morse potential that is shown here. So this potential has two terms. So one term is repulsive. So if the particle, they approach each other too much, there will be a restoring force, bring them back to some equilibrium distance. So this is the repulsion term. So on the other hand, so there is the second term here. If the particles go away from each other too much, there will be a restoring force as well, but now bringing them back to the original distance as well. And I'm fixing all these constants controlling the potential throughout the talk. This is also fixed here. This will not change during the talk. But this function, UGR, this is a two-dimensional function. This is a Mexican hat, right? So here we can show a cross-section of it, just to have an idea how it behaves. So we can see we have the minimum here. This is the optimal distance between the particles. If the particle, they get too close, there will be the restoring force. You see that this is very intense because this curve here is very steep. And we see if one goes away, if the particle goes away from each other, there will be also a restoring force, bring them back to this position, right? And this is asymmetric, showing that the repulsive interaction is much stronger than the attractive one, as we see here. So with this in mind, so we understand a little bit about the system, we can now move into some simulations of it. So I'm considering here 25 particles. I'm fixing also this constant alpha, the input of energy, and I'm also fixing beta, this dissipation of the system. So now for these parameters, depending on the set of initial conditions, I may go to two different states. So it's bistable system. And so for a given set of initial conditions, we are going to have this rotational state. And for another set, we're going to have the translational state. So let's see some simulations of these states. Oops. Can just start here. So here let me make it full screen. So they start, you see at the, sorry. Yeah, sorry for this. So they start, they interact with each other in an erratic manner. We can see that this whole collective, they are moving all together. What you see here is the velocity of center of mass. So it's still moving as a whole. But notice the erratic motion inside the collective. At some point, this collective will approach some final state around here. And then we are going to see that spontaneous order will emerge among the particles. Let's see, it's going to get there. Let's see the phase of this state in a moment. So you see you have some transients, the dynamics. This transient, I'm not showing today that it is chaotic, but it is chaotic. So here we can just say it is erratic, but I can anticipate that it is chaotic.
What are the colors?
The colors is only to distinguish one particle for the other. They are identical. Yeah, good question. So. Also, the diameter of the particles here are just to illustrate it. So what the controlling the distance is the potential itself. You can see now already forming some concentric rings. We are approaching zero of center of mass. Now we have these rings formed here. So the erratic motion disappeared, and then we have this collective state spontaneously organized itself, right? And now we have some order in the system. So one particle is in a given ring, it does not change to another. And this state is an absorbing state. So once we get into it, so we do not go away of it unless we perturb the system, right? So now let's see the other one. So I change only initial conditions from one case to another. So here I'm a bit with zoom out because I need more space in this area. But the particle again start with random initial conditions, and then they interact with each other now. But you see already that we have, for these initial conditions, we have more velocity or more energy in the translational mode. They are not rotating so much. They are moving more. And notice now that contrary to the other case, the center of mass is gaining velocity, as we see here. And they are interacting and looking for some static configuration. Let's see. So here they go offset a little bit. So sorry for this. You need to redo the simulation to fix this. But then finally, they find this state. Now they go to infinity in this crystallized form. Okay? So if you think about the functions of each state, so the first one, rotational one, the function of that state is to keep the collective parked somewhere in space. And the second one, the function of this state, is to move the collective along the physical space, right? So we have two functions performed by the collective, okay? So let me go back to the presentation now. But as I said, I want to apply a local control. I want to make interventions in only one particle in order to make the system perform a global transition. So now for us, the control will be the ability to go from one state to another. So we can go from the rotational state into the translational one, or vice versa, by applying a control which is local, only one particle. So we are in 25 here in this case, okay? And since we are in the physical state space, the natural intervention to implement here is accelerations, as we see here, acceleration, as we see here, and these perturbations A, that correspond to accelerating one particle, this is prescribed at delta V. This is a variation in the velocity of that particle, and this is implemented with some angle theta, as we see here. So if you want to have an insight about how this works, let's think that the particle is in the zero position here. I will apply this variation of velocity in a given theta prescribed by measuring with relation to the horizontal axis, as we see. And theta can vary from 0 to 360. So here's not the complete diagram. So another thing is important, prescribing the perturbation, as we see here, but also which particle to perturb. So here I'm going to implement one perturbation in a given particle X. It's a random particle there. I'll just choose one at random and see what happens for the moment. And also important thing is the timing in which I apply the perturbation. So this is applied at this time, 600 arbitrary units here of the system. So it's the same state as before, the rotational one. So let's see what happens. So we start the simulation in the rotational state. Let's make it big. If you look here, at some point here, you apply the kick here. So we were in the rotational state, and now I apply the kick. We enter, again, this erratic state, and the particle starts with moving in a erratic manner. You see they interact with each other with lots of energy, still in the rotational mode, but it's not so organized as already. So let's see what happens now. So they will take some time, but you can see here that now, instead of going back to the zero, they will go to some constant velocity of the center of mass. And I perturbed only one particle. This is the good thing. So they interact, and now you see larger and larger excursions in the physical space. And then, last one now, I would say. They go up, and then they find the other state. Now they move to space, they move through space in this crystallized form. So then we were able to get the system in one state, rotational, apply a local perturbation in only one particle, and make the transition to happen to the other state. So this is for us the local control part of the title. Okay? But now some questions come to mind. So the first one, so can I apply any intensity of the perturbation, delta V? It will always work? We don't know. Can I apply any theta? Any one would work? We don't know. Can I perturb any particle? We don't know as well. So to have now some insights about these three problems, I'm going to consider a smaller version of the system. So we want now, from now on, to answer these three questions, right? I get a smaller version of the system with three particles only, as you see here. I will perturb only one of them, the yellow one, the number one, the yellow. So here in the case A, I am initially in the rotational state, as we see here. So this is the x component of the position, is rotating. I apply the perturbation now at time 3000, as we see here in the yellow particle. We go into the erratic state again, and end up in the translational one. So in the case B, I am initially in the translational state. I apply the perturbation at time 3000. I go into the erratic motion, and then end up in the rotational state. So it works for 3 particles. But the good thing is now that the system is lighter, I can perform simulations with not only one perturbation, but a whole ensemble of it. This is what we do next. I consider an ensemble of perturbations for the same system, 3 particles. I get an ensemble of perturbations, delta V. So in the interval of 0 to 2, and I also vary theta 0 to 360, as we see. Once I get this interval, this kind of interval of accelerations applied at particle 1, this regards me these polar diagrams. So in these polar diagrams, I mark in white the perturbations that do not result in transitions. This is the white part here. And I mark in gray the perturbations that do result in transitions. So this is the gray part here. So then this gray part, we can regard this as the effective set of perturbations. Okay? We can see that if you look now at the angle, so it is prescribed in some angle. So this red arrow that we see here is the instantaneous velocity of the particle. You can see that this effective set is always opposing to the velocity of the particle. If this moves in some direction, I have to perturb backwards in order to cause the transition to the other state, right? So this is the important thing. And this is in A is for the rotational state to the translational one, and in B is the case, the vice versa, the contrary. So I start in the translational state and go to the rotational one. Again, so we see that also the effective set is opposing the direction of motion of the particle. Okay? This is a good thing. So another thing is to notice here that the boundary between the gray points and the white points seems to be non-trivial here. So this is a fractal boundary. So I'm not showing here today as well, because we have no time, but this means that erratic motion that we see here, so this is coming from a chaotic saddle mediating the transition between the 2 states. So these 2 states, they coexist, but in between them, there's a chaotic saddle that enables one to apply the perturbation in one state, reach the chaotic saddle do for you the work, brings you to the neighborhood of the other state. So you save control energy by doing this. You take advantage of the chaotic saddle, right? And this is what we see from these fractal basing boundaries here. So another important thing to note is here, for the rotational state, so this red arrow, if I change the particle, if I perturb another particle, so this means that this arrow will change, right? Because from particle to particle, so the arrow changes direction. So this means that for different particles, the orientation of the effective set will also change. Just to have this in mind. And this do not happen with the translational state, because they are all moving in the same direction, right? So with this, we can have some insights about the minimal amplitude to cause transitions that we see here. There is a minimal amplitude. And we also have insights about the angles, should be opposing the movement, right? Now, it's missing to have some insights about on which particle to perturb. So let's see that now. So to understand that, you consider 6 particles now, only 6. And here, in this slide, I have transitions from the rotational state to the translational state, right? So here we have polar diagrams, as before, but for each one of the particles. So this means for the blue particle, I start the system. At time 3000, I apply the perturbation and obtain one polar diagram. And then I replicate the simulation. Identically, I start the simulation again, and at time 3000, I perturb another particle, the orange one. And do this for all 6 particles. As we expect, we are in the rotational state. This means that the effective set is changing directions, right, from particle to particle. But this is not important here. The important thing is the density of points. Notice that the effective set is much more dense in the blue particle than in the red particle. So this means that it's much easier to cause transitions if I perturb the blue particle, not the red one, right? So, and this indicates that there is also some hierarchy inside the collective. So this hierarchy to cause transition to the other state. So this is an important thing. So, and now for the translational state, so now we see that the effective set is not rotating, but the density of points is still different, right? So if you look at the red set, it's much more dense than the yellow one. So again, we have some hierarchy inside the collective. Now it's a different collective, it's translational one, and this hierarchy is to cause transition to the other state. So since we have now these hierarchies and we have these self-organized states, they are spontaneously organized, the question is, where in the collective is the particles that are higher in the hierarchy? Because we can compute this now easily, right? Because we have the hierarchy, we have the collective, and we have the format, the steady state, we can compute this. And this is what we do. So just before that, I need to define a measure to quantify the density of points of the effective set. I call this control effectivity, this epsilon. So this is nothing more than the density of points of the whole set corresponding into the effective set. So this is, I apply a number of perturbations for the whole polar diagram, and a fraction of these perturbations will be effective. And this fraction is my epsilon. This is just like this. So as the particle is higher in the hierarchy, bigger the epsilon. And now for the rotational state, so here we have 16 particles. They are rotating here with the concentric rings, as we saw before. We notice that particles that are high in the hierarchy, they occupy the external ring of the formation, the outer layer of the formation. In order to see if this is not just coincidence, we replicate the simulation for different sizes and consider different realizations with the differential conditions for every size. And we see indeed a pattern is formed here. So particles in the outer layers, so they are high in the hierarchy. So, and now, for the translational state, so they are moving here to that direction, to the northwest, right? And we see that particles which are high in the hierarchy occupy the axis transversal to the movement, as we see. To see if this is not just a coincidence as well, we replicate it for different sizes and some realizations of for each size. And now we put all of them move upwards here, and we see the pattern formed here. So they are mostly along the axis transversal to the movement as well. So this answers our third question, which particle to perturb? So there is a pattern for this, right? And this brings me to some take-home messages. So what we have seen first is that it's possible to realize local interventions in a standard system and cause global transitions. So this is the first thing. The second is that the control effectivity, the ability to go from one state to another, it's not equally distributed among the particles, but there is some internal hierarchy. And third, we see that particles which are higher in the hierarchy occupy some special positions in the collective. So with this, I thank you very much for the attention. So, yeah. So some questions.
Okay, thank you very much for the talk, being right in time. Do you have some questions in the audience?
Thank you for the lecture.
Yeah.
First, if I am in the rotational state, I do the perturbation, go to translational, and vice versa.
Yes.
What happens if I do a perturbation in the chaotic state?
Sorry,
What happens if I perform a perturbation in the chaotic state, on the saddle?
In the saddle. The saddle is unstable itself.
Yes.
So if you go there, you will escape from one state to another. You don't need to perturb to escape. But if you perturb, you may as well postpone the escape or advance the escape. This you can do. So that's the overall outcome of this. So this is what is known already. So you would escape, but it's possible to suppress the time that you stay in the chaotic saddle by applying the perturbation. So this is done for heart dynamics, for example. It's known that you have this coherent pumping in the heart, and there's a chaotic saddle there as well. So if you go to the chaotic saddle, the pumping is incoherent. So you don't want that. So then you apply perturbations to suppress this incoherent movement in the chaotic saddle. So you can advance the escape So, and go back to the coherence states.
So necessarily you go to one state or another. There's
Yes,
not
you
a
have to
third
go
state.
because it's unstable. It's unstable chaotic set.
Okay.
So,
And a second question, that model that you used in the first equation,
yes.
it's like some generalized Fitzhugh-Nagumo model because it has like a third term.
This is something. Sorry, backwards. So the Fitzhugh-Nagumo model is a model for phases.
Yes.
So you can use it for different things. So, and this is a model for amplitude. So we have really the velocity and the position here. So you could extract approximations from this model by looking only into phases of this model. And you could do this, you could get this equation, look into only the phases and see some Kuramoto analog there.
Okay.
But this has difference is that. So one is only for phases, and this is more complete. So because you have also the amplitudes, not only the phase, but one can model this thing with some looking only to phases by something like Kuramoto. Yeah.
Thank you.
It's possible. Yeah.
Any other question?
So very, very nice talk. Thank you. So I would expect that when you kick your system off the stable state
Yes.
into the chaotic saddle, it would equally likely go back to its own state or to the other one.
Yeah.
So, and in that case, that is not really control, right? It's
Yeah.
a 50-50.
50-50. And
Yeah.
this is true.
It's true.
It's true, because one can see this here, for example. So more or less half
it's
of
half
the perturbations stay white because you perturb, you may go to the chaotic motion, but you end up back in the original one.
Okay.
So it's true. So you save energy by taking advantage of the chaotic saddle, but it's not certain that you are going to have the control.
Okay.
Because you can go back. Yeah,
Thank you.
this is true.
Everton, one short question. Any
Yes.
idea where this hierarchy is coming from?
So where they are coming from?
Yes.
So this is a good question indeed. So we have some conjectures about this. So it seems for this particular case, for example, so the particles in the outer layer, so once you perturb them backwards, so they are the ones that are feeling less the attraction of the center, let's say this way. So it's easier for them to escape because they have no neighbors from one side, for example. Could be something like this, but this is not for sure. So this is still something to investigate. And this also violates the second case because the transversal axis, the middle one is also causing transitions. So somehow you cause some asymmetry by perturbing this, and then it's easier to cause the transition. But it's not clear yet. We don't understand yet why this is this. Yeah. Could be. Could be. I could change the potential now and also play around with more parameters of the potential. This is not what comes to realize in the future, but this is a good question. So we don't know exactly why it's like this, but seems to be statistically robust. So it seems to be really a pattern there, but there is no explanation yet. So yeah, it's a good question. Yeah.
Building on this question about the potential,
Yeah.
how sensitive is these two states? How much do depend on the parameters that you choose? That's one part. And the other
Yes.
is, I can understand that in the translational mode, particles need to be in the minima of the effective potential.
Yes.
It's
They
not
will
so
be.
clear. How do you understand the rotating case? Because it's not so obvious how the potential interplays with this motion.
So even though, this is a good question, even though the potential is pairwise, right? So they are acting particle by particle. So I cannot show. So for this case here, which is the most symmetric case, so the distance between the particles, either in the translational state or in the rotation, they are more or less in the minimum of the potential. But as you put more particles in the system, so you don't have that control for the rotational state. So there is some kind of arrangement inside of the particles that finds itself the suitable way that takes into account the number of particles as well. So it's like you share this optimum distance with all other particles to find some equilibrium. So, but this is also a good question, yeah.
And it will remain.
Yeah.
is it very sensitive to the size? If you keep on increasing the number of particles, the two states would still remain in the thermodynamic limit?
Yeah, so this is also important because the size would be a perturbation to the system as well. So if I am in the rotational state with a 3 particle, if I put one more particle with the new initial conditions for this particle, it could perturb this state, and then they go to the translational one. So yeah, I cannot guarantee if I'm increasing, I stay in the same state. Yeah.
Okay, any other question? Okay, in this case, just let's thank again the
Thank
speaker.
you.
So now we move to the next speaker,